How telescopes are made. Telescopes, also known as astronomical telescopes, are optical instruments that help humans observe objects at great distances. They are widely used in various fields such as astronomy, maritime navigation, aviation, space technology, and military reconnaissance, making them an indispensable tool. Historically, the first telescopes were created using optical instruments to capture light from distant objects and produce magnified images, making them easier for the human eye to observe. These were known as optical telescopes. Later on, other types of telescopes were developed that utilized different forms of electromagnetic radiation, such as radio waves, infrared, ultraviolet, X-rays, and gamma rays to observe distant objects in the universe. These advancements have expanded human capability to observe and understand the universe, from distant stars to mysterious astronomical phenomena. If you have ever attended a club star party or an amateur astronomy convention, you've undoubtedly wandered through an observing field filled with the silhouettes of telescopes and the hum of enthusiasts exchanging tips and experiences. Scattered around, you'll see various telescopes, some drawing small clusters of onlookers, while others have crowds eagerly waiting for a turn to view the current celestial target. Often, the most popular are the large aperture Newtonian reflectors, whose eyepieces reveal details invisible to lesser instruments. Whether it's the intricate labyrinths of a bright nebula, the dazzling spectacle of a star cluster, or the faint glow of a galaxy on the edge of perception, these magnificent telescopes elicit more oohs and ahs per inch of aperture than almost any other. At the heart of these outstanding, handcrafted instruments are their optics. The mirrors inside these telescopes are painstakingly and individually crafted by optical artisans. They blend state-of-the-art fabrication techniques with personalized testing to ensure each mirror is near perfect. To understand the process behind these exceptional mirrors, I recently interviewed the owners of several manufacturers of premium optics, including Lightholder Optics, Optiques Fulham, Ostahowski Optics, Weight Research, and Zambuto Optical. Each owner shares insights on how they began their careers and the specific techniques they employ to create their masterpieces. These magical mirrors are crafted in small optical shops by individuals who often stumbled into the business by chance. Some had mentors early on who played a crucial role in helping them hone their skills. Carl Zambuto of Zambuto Optical credits a local amateur telescope maker, Earl Watts, with convincing him to make his first mirror, a 6-inch. I had zero interest, but he persisted, so I made the first one and it hit me like a disease, he says. The following weekend, I was creating another one outside on a snowy day at my parents' home in the mountains. Fulham, however, made his first mirror out of necessity. I could not afford my first telescope, so I decided to make it myself, he says. Despite different motivations, the outcome was similar to Zambuto's. The results were so gratifying that I decided to make a second one and then another one. As these amateur telescope makers share the views through their telescopes with friends and fellow enthusiasts, the demand for custom mirrors grew. Initially, things started slowly. However, as their reputations for quality spread, so did their businesses. The process of making candy, much like crafting telescope mirrors, is an intricate art form. From boiling sugar to shaping and coloring each piece, every step requires meticulous attention and skill. Controlling temperatures is crucial to avoid negative impacts on the candy's color and shape, while precision in pulling and cutting ensures perfect pieces. This process not only demands patience and creativity, but also emphasizes the importance of maintaining and caring for tools and machinery. Everything is done with care and attention. The lessons from making candy and crafting telescope mirrors are profound. Both processes teach us about patience, creativity, and the importance of attention to detail. They also highlight the significance of preserving and passing down artisanal techniques from one generation to the next, ensuring that our heritage remains respected and continues to thrive. Through these endeavors, we are reminded that whether we are gazing at the stars or savoring a piece of candy, the dedication and craftsmanship behind these creations make our experiences truly special. To begin the process of crafting a high-quality telescope mirror, a new mirror blank is carefully ground down to form a precise parabolic curve. This initial stage, known as grinding, involves pairing the blank with a grinding tool, typically made from glass, plaster, or ceramic. Unlike conventional sandpaper, the abrasive used in this process is a mixture of grit and water. A layer of grit is sprinkled onto the mirror blank, then water is sprayed over the grit, and the grinding tool is set into motion by a machine. As the grinding progresses, additional grit and water are applied as needed. Coarser grit speeds up the grinding process, but results in a rougher surface, so it is crucial to frequently measure the curve's depth to ensure accuracy throughout the process. After grinding, the mirror undergoes polishing, where the initial concave curve is tested. For high focal ratio mirrors, typically f10 and above, a spherical concave curve might suffice. However, lower focal ratio mirrors, particularly those in today's fast sub-f4 Newtonian systems, require extremely smooth and precisely crafted parabolic curves to focus light correctly. This necessity leads to the process of figuring, which fine-tunes the mirror's surface. Figuring involves using a second tool called a pitch lap, which is passed over the rotating mirror by hand. The polishing compound used in this stage allows for very fine adjustments to the curve. This is where the craftsmanship truly shines. Through meticulous testing and inspection, followed by gradual corrections to any hills, valleys, or irregular zones in the parabolic curve, artisans achieve exceptional results. Initially, machines perform the bulk of the work, but final adjustments are often made by hand. To ensure the mirror is free from optical imperfections, it undergoes several tests using interferometers in controlled environments. Interferometry testing involves comparing the new mirror against a reference mirror with known accuracy. A laser beam is directed between the two mirrors, creating interference fringes on the mirror's surface. These fringes are analyzed by a computer, which averages the results from multiple tests to determine the mirror's accuracy. Manufacturers like Terry Ostahowski of Ostahowski Optics often provide a computer-generated report to customers, objectively verifying the mirror's quality. Once the mirror is accurately shaped, the final step is coating. Some premium mirror makers send their products to specialized coating companies, while others handle this step in-house. Most premium mirrors are coated with enhanced aluminum, which reflects 96% of the incoming light, compared to about 90% for standard aluminizing. The reflective coating is applied in a vacuum chamber, where aluminum is evaporated into vapor and evenly deposited onto the mirror. To achieve an enhanced coating, several layers of dielectric film are added atop the aluminum. Finally, an overcoating of silicon dioxide, SiO2, is applied to protect the delicate surface from scratches. This coating is both hard and transparent, ensuring the mirror remains durable and effective. The entire process of making a telescope mirror is a blend of precision engineering and artistic craftsmanship. From the initial grinding to the final protective coating, each step requires skill, patience, and meticulous attention to detail. This dedication to excellence ensures that each mirror not only performs superbly, but also stands as a testament to the artisan's expertise and care. Mirror blanks usually start as either molded blanks or glass that is water jet cut from flat sheet glass, explains Gordon Waite of Waite Research. We have developed a computerized, high-speed, rough polishing machine programmed with a series of strokes to move the mirror smoothly toward the desired surface shape. This fine-tuning continues up until the final moments of finishing a mirror. For Carl Zambuto of Zambuto Optical, the process is all about control. This is a two-person shop. We use simple tools and machines that we built ourselves. This allows them to control every aspect of mirror manufacturing, from casting the mirror blank to toughening the glass through heating and slow cooling, to grinding, polishing, figuring, testing, and coating. Zambuto's specialized machines offer an added bonus. Each machine has only one job in the process, allowing us to build the mirrors at lower cost, he says. John Lightholder of Lightholder Optics takes a slightly different approach by starting with pre-generated blanks, saving time and increasing operational efficiency. After obtaining the blank, he cuts and polishes the mirror's edges in a process called beveling, which ensures the edges won't improperly scatter light. Next, he says, is grinding with 40-micron aluminum oxide grit. Optiques. Fulham, led by Normand Fulham, has produced some of the largest mirrors, including a massive 61.25-inch f3.5 optic. For mirrors larger than 24 inches, Fulham employs his unique techno-fusion blanks. This innovative fusing process allows him to create very large, rigid mirrors that are surprisingly lightweight for their size. No matter the technique, the end result is a mirror that, when placed in a finely crafted telescope, is sure to elicit oohs and ahs from anyone who peers through the eyepiece, especially the proud owner. Each mirror is a testament to the dedication and skill of its maker, reflecting not just light, but the culmination of meticulous craftsmanship and innovative engineering.
That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.